Hello everyone, I'm Lazare Osmanov from Team Georgia, and today I'll present problem number 5, Sweet Mirage. Fata Morgana is the name given to a particular form of mirage. A similar effect can be produced by shining a laser through a fluid with a refractive index gradient. We have to investigate the phenomenon. But at first, let's talk about Fata Morgana. Fata Morgana is the kind of a mirage which we often see on the beaches and in the desert, because in these places there is a temperature gradient in the air, which causes the refraction index gradient too, because refraction index is dependent on the temperature. So finally, the trajectory of the ray, which comes from some object to our eye, doesn't have a linear shape because of the refraction index gradient. Its shape is some kind of curve, and finally our eyes see this kind of imaginary position of the object, which is a little bit higher than the real position of it. The same effect could be done by just dissolving a sugar or salt inside the water container, because after some time, when we have a steady state situation, when we just shine the laser through it, because of the refraction index gradient, and which is caused by the gradient of the concentration of sugar or salt, we will have this kind of curve. We could see the same view as the experiment. And on the first GIF, we see how the final destination of the laser beam is dependent on the laser position and the inclination angle of it. And we also conducted the same experiment by using different wavelength lasers. We also conducted an experiment when the final destination of the laser beam was out of the container and not inside of it. And I will talk about it later, why we conducted this kind of experiment and what kind of result we got from that. But until that, uh, we have to investigate the trajectory of the laser beam. So for that, the first part is to write the Snell's law. The reason why we do that is because we need to have some kind of function, some kind of dependence between the coordinates, the y coordinate and the x one. So we just connect sine alpha to the cotangent alpha, as we know that cotangent alpha is the derivative of the y coordinate by x. The second step is to calculate, to investigate how the concentration is dependent on height. And we do it by using this formula, which is the just diffusion equation under the gravitational field, where the d is the diffusion coefficient and s is the sedimentation coefficient. So sedimentation coefficient is just ratio of the mass on the Dirac coefficient, and the Dirac coefficient is just dependent on the shape of the particle, which is sphere in our problem. And we calculated the diffusion coefficient by using a Einstein-Stock formula. But actually, when the sugar is fully dissolved inside the water, we wait like for 7 or 8 hours in order to have a steady state situation inside of the container, the water container, in order to have zero part, the first part of this equation to be zero, because as we know, after some time, when the concentration on each height is the constant, then it means that the concentration derivative by time equals zero. So after that, this equation becomes really simple to integrate and finally define the concentration, how the concentration is dependent on height. And on this graph, we see how the concentration of sugar and salt is dependent on height, of course, qualitatively, to see that they are dependent exponentially. And the final step to investigate the trajectory is to connect the refraction index and the concentration. And for that, we use this kind of experimental measurement. We just stir the sugar inside the container in order to don't have any kind of gradient inside of it. And then we shine the laser through this container. And then we calculate the distance between the first and the second beam, which is x right here, and the x will be, of course, dependent on the concentration. So we conducted the same experiment for different concentrations and calculated each distance between the first and the second beams. And then by using just the Snell's law, we connected a refraction index and the distance. So finally, we tracked experimental graph of the refraction index dependence on concentration, and we got that the refraction index is dependent on concentration linearly. And on this graph, the green line is the same dependence for the green laser beam, and the red one is for the red laser beam. So after we have all these three equations, the first one is just the Snell's law where we have the coordinates. The second one is just concentration distribution by height. And the third one is linear dependence between the refraction coefficient and the concentration. After combining these three equations, we have this final differential equation, which we have to solve in Wolfram mathematics, and finally get this theoretical line. And as we see, and on this theoretical line, we also see experimental dots, which fits to our theoretical line. Every point fits to our theoretical line. This is the same experiment, but for the different data. So after we know what is the trajectory of the laser beam, now we have to think about where is going to be the imaginary position of the laser beam or whatever object we see from another side of the container. And the and we did it by using also Wolfram mathematics, because we just calculated where the two beams from the same point were going to be, and finally when they meet each other, there is going to be the lower and the higher points of the laser beam. So finally there is going to be the imaginary position, and which we theoretically investigated that it is dependent on the inclination angle of the laser beam and the laser position of it. And the result is that the lower the sine alpha and the higher the laser position is, we have the higher imaginary position of whatever object we look at. For example, and for our case, it's laser beam. And this is just the same result, but on the two-dimensional graphs in order to have a comparison between the theoretical line and experimental dots. And as we see, every experimental dot fits to our theoretical line. Okay, after understanding the trajectory of the line and just the mirage, I mean the imaginary position, where is going to be what is dependent on. Now we could talk about the further insights of this problem. And the first further insight is the question of why do we see this kind of shining of another part of the water? And the reason of it is really easy one to understand. As we know from the Fresnel, when the light hits to some surface, some part of it just reflects and another part is goes away. So with the part which goes away is just the trajectory line, and another part which is reflected is the shining part of the water. And we just calculated what amount of what amount of energy of electromagnetic wave, I mean the light power was reflected, and how much was going on as the trajectory line of the laser beam. So after that, we could talk about the lensing of the rays. So we just thought that this kind of system could be some kind of a lens, and if it's some kind of a lens, then we have to understand what kind of lens is it, where are the two parallel beams going to meet each other, and we just have to investigate everything about it. So theoretically, we just shine two parallel beams to this container. The container thickness is really small in order to have a linear trajectory inside of the container of the light beams, and then we just have to observe where are these two beams going to meet. So as we see, these two beams will never meet each other on the right side, which means that this kind of a lens would always be a biconcave lens. So now we just have to calculate geometrically where are these two beams going to meet. And for that, we use a simple geometry, a similarity of the triangles over here, and finally calculate the values which we need to use in this formula. And this formula is written for the biconcave lens. And as we said that this kind of this is a biconcave lens, then it is possible to say, and it's possible to calculate where is the focal length going to be. And from this equation, we could calculate the focal length, and the result was that the focal length is mainly dependent on the concentration, the primal concentration of the sugar inside the water, and the temperature of the water too. And the result is that the higher the temperature and the lower the primal concentration is, further the focal length we have. And it's a very logical thing, because the higher the temperature, then it means that there is if the temperature is high, then there is not going to be a strong gradient of the refraction index, which means that these two beams will meet each other in the infinity. And this is very logical result. And finally, I think now we could conclude. Oh, sorry. Now I will talk about the two-dimensional diffusion, which could be caused by just rotating our container, which means that there is not going to be only gravitational force, but there is also going to be a centrifugal force. So we just calculated, we just wrote the same two equations for the centrifugal force and for the gravitation, and finally have the profile of how concentration is dependent on the radius and height. And this is just 3D graph where we see how concentration is dependent on height and radius. But we didn't conduct this experiment because in order to have this kind of difference to see visually, we needed high angular velocities. And under high angular velocities, it was impossible to conduct the experiment. And finally, I want to conclude everything. We calculated at first concentration dependence on height, then we connected refraction index and the concentration, finally defined the curve of the laser beam, and we solved it in the Wolfram mathematics. After it, we calculated the imaginary position and what was it depended on, then the focal length, after we proved that these two beams would never meet each other, and then we investigated also Fresnel's reflections and two-dimensional diffusion, just theoretically. And these are the main results in our problem: concentration, distribution, refraction dependence on the concentration, and the final trajectories of the laser beam. Imaginary position was investigated too, and also focal length. And finally, thank you for your attention.